first thing I like to do is to get a brief review of last week's class. Okay, did you guys try the online quiz? Okay, I guess for the multiple choices part, it's pretty straightforward, and the feedback will be just A, B, C, D. And just for the questions part, they ask for the objective functions and x1, x2 value. As I said, as long as your values are correct, even if due to technology limits, if it didn't grade you correctly, that still be fine. Okay. This week I got an optional exercise for you guys again that takes the similar format of what will happen for your homework assignment that's coming in a week. So in that one, the solution I already posted, but please don't look at the solution before you do the homework problems. Okay, same as those class examples. On Moodle, I post all the class slides, but that's only for review purpose. And I said, do not look at the slides, especially the solutions, before we go through the problems. Because for all the OR problems, once you see the solutions, it's pretty clear. It makes sense. Okay, but how to get those models is what we're going to learn in this class. It's the thinking process that is very important and difficult. Okay, and let's review what we studied last week. Okay, last week is the first week, and we did the introduction, what OR problems applications are, and there were some videos for you to watch online. And first, let me ask you some questions. What are the three components of every OR model? Think about it. Decision. Okay. Okay, variable. The decision, right? The decision will be like say how many products to make, how many hours to schedule workers, how many of each type to make. So decisions. And there is always the objective, whether to minimize the cost, maximize the profit, minimize the risk. Okay, and then we said all the OR problems exist because we're dealing with limited resources, and those limited resources are translated into constraints. Okay, and we write the objective functions and the constraints in the formula of those decision variables. Okay, and if the formulas are linear, what do we call the model? Linear programming, right? Okay, LP, that's the LP model. So if all the objective functions and the constraints are linear combinations of the decision variables, we call them linear programming. Okay, and we differentiate them because we use different algorithms to solve those problems. Okay, and we like all the problems models to be as linear as possible. Okay, then we talk about how to graphically solve those LP problems with two decision variables. Okay, let me ask you again. What defines the feasible region? Remember, we draw x1, x2 to coordinate. We draw a feasible region. What defines the feasible?
Constraints are satisfied in the feasible region.
Okay. So the constraints define the feasible region, right? We draw a line based on the formula of each constraint. If it's greater than equal to, less than equal to, we just translate into equal to equation, and we draw the line. If it's less than equal to, then it's area under it. If it's greater than equal to, then it's area above the line. Okay, and the region where all the constraints are satisfied means all the regions that overlap. Okay, that's the feasible region. Why do we call it a feasible region?
It's a feasible solution, maybe not optimal.
Okay, because all the points in that feasible region will be a feasible solution to our problem. Okay, feasible solution means it satisfies all the constraints. Okay, and if we use level curves to find optimal solution, what defines the level curve? Or which part of the model is associated with the level curve? Objective function, right? Okay, constraints define the feasible region, and we use objective function to find the slope of the level curves. Remember that? Okay, so once the slope is identified, we'll draw one level curve within the feasible region. And depending on whether the objective is to maximize or minimize, we move the level curve within the feasible region until it touches, most of the time, touches a corner point that maximizes the objective function value, which is intercept on the vertical axis. Okay, and if it's a minimization problem, then we find the minimize the intercept, but by moving the level curves. Okay, and once we identify that corner point, we say, okay, which two constraints intersect at that point, at that corner point, and we find the x1, x2 value. Okay. And there is another way to identify optimal solutions besides using level curve. What was that? What's that? Enumerating the corner points, right? Right? Yeah. Okay, and because we know that the optimal solution always occurs at the corner point. So we just enumerate all the corner points, find out what the objective function value is at each corner point, and we compare them. So if it's a maximization problem, then we find the corner point that gives the biggest objective function value. If it's a minimization problem, we find the minimum value. Okay, okay. But enumerating the corner points does not work in a special situation. What is that?
Unbounded.
Okay, when the problem is unbounded. That means there is a place where there is no corner point. Okay, so you may be able to enumerate the sum of the corner points, say the 0, 0, and the one on the x1 axis and the one on the x2 axis. But because the problem is unbounded, it goes all the way to, say, infinity. Okay, then you won't be able to identify a corner point. Okay, so using the level curve is a preferred way to solve LP problems graphically. Okay, and when it's confusing when you're comparing two corner points, adjacent corner points, you don't know which one is the optimal because the slope of the level curve may be very close to one of the constraints. You don't know whether it's the points above or below. Then you can use the method, calculate the objective function value given at the 2 points, see which one is the best one. Okay, but using the level curves at least help you identify the 2 points that you are comparing with. Okay, then we talk about some special situations in LP models. Okay, unbounded problem is one. Okay, so what are the other ones? Redundant what?
Constraint of variables.
Okay, a redundant may become redundant, right? What is a redundant constraint?
It does not have value in decision making, finding the optimal solution.
Okay, okay, very close.
So the constraint is outside the feasible region.
Okay, okay. When a constraint does not play a role in defining the feasible region. Okay, it's outside the feasible region defined by the other constraint. So that means that constraint will be satisfied no matter what. Okay, so that constraint is redundant. Okay, so that's one special situation, and we talk about the unbounded. What are the special situations we talk about?
No solution one.
No solution one, okay. Very non-technical. Now solution one means what?
That two constraints are mutually exclusive, or one
Okay.
excludes the other, and so there's no ability to satisfy both constraints.
Good. No possibility to satisfy all the constraints. So that problem becomes infeasible. Okay. So that's so there is no feasible region, so that means infeasible, the problem. Okay, the third one. Okay, good. Anything else? Special situation? Okay, there could be alternative optimal solution. When does that happen?
So the line, all the points will be the alternate solution, right?
Okay, all the points on the line.
Yeah.
But when does that line become the feasible, the optimal solution? When it overlaps with one constraint, right? Do you remember that? Alternative solution. Okay. When the level curve has the same slope as one of the constraints, and it happened to be that that level curve, when the level curve overlaps with that constraint, all the points on that overlapping area give the best optimal give the best objective function value. Then all the points on that line becomes alternative optimal solution. Okay, but it does not always happen like when it does not mean that when the level curve has the same slope with the one constraint, you will have alternative solution. Okay, it's not the other way. It's when they have the same slope and at the same time, all the points on that line gives the best optimal objective function value. Okay, it could be, say, the optimal objective function value occurs at a corner point, but the level curve has the same slope with one of the constraints. Okay, that makes sense? Okay, anything else we talk about? Special conditions?
The optimal solution can be a point.
Okay, yeah, so just now, we talk about alternative solution and the line. All the points on the line are optimal solution. Okay, before that, the feasible region can be what? A point or a line, right? Okay, when does that happen?
All the constraints assessing one point.
Okay, so when all the constraints just intersect at one point, that means all the constraints are not inequalities, but they are equations, right?
Yeah.
Okay, so when all the equations are satisfied, they intersect at one point, and only that point is a feasible solution, at the same time the optimal solution. So at that time, regardless of the objective function, you only get one solution. Okay, and before that, we talk about the feasible region can be just a line instead of an area. Okay, when does that happen? Think again.
When one of the constraints is equal to some value, not less
To some
than
value. Okay, so one of the constraints is an equation, right?
Yeah.
Okay, so if in the constraint there are some inequalities, but one of the constraints is the equation, then that equation defines a line where the line is within the feasible region defined by the other constraints. That part of that line becomes a feasible region. Okay, and all the points on that line becomes a feasible solutions, and you will find the optimal solution on that line. Okay, so these are the special situations we talk about, and in the optional quiz, you're asked to do some exercise, and this week you are asked to do some more exercise on how to solve the problems graphically. Okay, so practice that. Okay, so with that, we're going to continue to this week's class content.